Hello and welcome to this final lecture on computer-aided engineering design. This is lecture number 40. What I plan to do is give you a brief course summary. I'll talk about how to use the course material that we have covered in the previous 39 lectures, and also I'll discuss different avenues which you can explore in future. So essentially, we had studied only geometric modeling as a part of this course. This is the layout that you see on the slide. The first column is about solid modeling that we had discussed. The second column, or the middle column, is the design of curves, and the third column is the design of surface patches. I have a confession to make here. Although we had discussed only geometric modeling as a part of this course, CAD, computer-aided engineering design, involves quite a bit. It's not only geometric modeling that we talk about in CAD. So I was having a hard time trying to arrange the material for this summary lecture. And I'll talk about that as we move along. So we studied, or we actually started with this course by this cartoon here. A common person surrounded by different products. Essentially, we talked about technology, and we talked about how technology is getting more and more complex to simplify a common person's life, and how computer-aided engineering design plays a very vital role in defining the technology. We also had discussed the design process. The design process involved iterations between parametric or geometric modeling, analysis of the model or of the form, and modification of the form to improve the design. And to automate this iterative procedure, we needed a computer. And therefore, this was computer-aided engineering design. As a part of this course, in the previous 39 lectures, we only touched upon the top circle, that is, geometric modeling. We did not talk about simulation techniques, or we did not talk about how we can modify the form of a product systematically. There are different dedicated courses in these two major areas. So that is something that students and teachers should both keep in mind. The design process that we had discussed and that we had also practiced as a part of the workshop was an 8-stage design process. In the workshop, we had implemented that design process to design a lamp, a table lamp. Now, you would be having questions pertaining to hows and whys with regard to the design process. Here are a few questions that I will be posing on your behalf, and I'll be also trying to answer them. Why study a design process? Computer-aided engineering design does not make sense unless we understand the significance of the term design. Why only this process, or this 8-stage process? Well, there can be many other design processes, but there is no doubt that a design procedure by nature is iterative. So students and teachers are free to explore different design processes which are available, and they can practice them at will or freely. If they like the design process that we had discussed as a part of this course, that's wonderful. If they don't, that's even better. They can and they have to be comfortable with a design process they choose to work with. How can one learn or teach this course? Well, a colleague of mine, Professor Justin Herder from the Delft University, asked me this question when we were attending a conference together. What came first? Was it the steam engine or was it thermodynamics? Well, the answer is quite obvious. It was the steam engine that came first, and thermodynamics as the theory behind the steam engine developed much later. Teachers and students may have their own methods or styles of comprehending a subject matter or teaching a subject matter. I would request both communities to adapt this course material accordingly. I personally emphasize learning by doing, so I use a two-tier approach. In the first tier, I encourage my students to build anything of interest to them. I want them to fund their own projects. I want them to get their hands dirty. I think that is a much better way to learn a subject matter. They can follow the design process that we had discussed, or use an alternative design process if they are not comfortable with this design process. I encourage my students to also use solid modelers, but I personally do not patronize any commercial solid modeling software. In the second tier, I try to familiarize my students with the rigor and the mathematics involved at the back end of the existing commercial solid modelers. Now, let me summarize the solid modeling techniques that we had studied in this course. That is the first column in our layout, shaded in black. I started off with designing two very simple components, a spring and a bolt, using an existing solid modeler. I will not name it. And I emphasized that many more complex designs are possible with existing solid modelers. We went on to study different properties of solids: boundedness, boundary and interior, boundary determinism, homogeneous three-dimensionality, rigidity and closure. Of these, boundary determinism was actually a property that set the base for this course. In simple English, this property essentially says that you draw any curve on a plane. That curve needs to be simple and closed. That should not be self-intersecting. And that curve would divide a two-dimensional plane into two regions. One region will be lying inside the curve, and the other one will be lying outside the curve. You can extend the same concept to three-dimensional Euclidean space. Now you have a closed, simple, orientable, bounded surface. There would be a region inside the surface, and there would be a region outside the surface. In a sense, this fundamental property about solids gave us a very significant clue, or a very important clue. Solids should be represented and in fact stored as simple, closed and orientable surfaces. This actually formed the backbone for our solid modeling or geometric modeling techniques. We studied homeomorphism, topology of surfaces, invariance of surfaces, wherein we considered the number of boundary components, orientability, genus, Euler characteristic, and connectivity number of a surface. And then we came to the main classification theorem. This was another very critical step in our course. The theorem essentially states that every closed surface is homeomorphic to a sphere with some handles or crosscaps attached. We had seen a nice cartoon of how a torus gets transformed into a coffee mug and vice versa. and that is what I meant by handles. So, every single surface is one of the following. It is a sphere, it is a connected sum of tori, or it is a connected sum of crosscaps. Since we are not dealing with self-intersecting surfaces, for us it is the first two, either a sphere or a connected sum of tori. It was the Jordan's curve theorem and the main classification theorem that actually set the platform for us to discuss solid modeling techniques or geometric modeling techniques from then on. Accordingly, we considered three representation schemes and modeling schemes: the wireframe approach, the boundary representation scheme, and constructive solid geometry. The wireframe models had problems. Since they did not store the face information or the face topology information, the corresponding models were ambiguous. We had seen this example. To take care of that, in the BREP approach, we had discussed something called the winged edge data structure. Here, we associated two faces with the base edge, and we stored all pertinent topological information for the base edge. In this example, the base edge was 3. Moving on, we also talked about make and kill groups. This was in reference to the Euler-Poincare formula that we had studied. That formula was true for all polyhedral solids. In a sense, for valid polyhedral solids, the Euler-Poincare formula was true, but the converse was not true. Anyhow, the details are there in that corresponding lecture. We talked about make and kill groups, M XYZ and K XYZ, and with these groups, we actually constructed a polyhedron from a different polyhedron. And then we talked about constructive solid geometry. We could have combined different primitives together to design a new solid model. These primitives would have been either standard or they could have been user defined. The combination operators were essentially set operators like union, intersection, addition, and subtraction. We considered the design of a bolt and associated that design or different features of that bolt with the history tree. Each node in the history tree represented a design feature for a solid. You would also have now questions pertaining to hows and whys of solid modeling. Let me again pose some questions on your behalf and try to answer them. Why study topology? As I said, the extended Jordan curves theorem and the main classification theorem formed the backbone of the geometric modeling techniques that we had studied in this course. Motivating oneself with regard to the hows of this course will be a bit difficult, I think, unless the basic topology is understood. I had covered only a bit of topology as a part of this course. The field topology, if students and teachers are interested, can be explored in a lot more detail if that is necessary. At the end of the first column, we talked about transformations and projections, different techniques, different methods. We first defined what transformations were. They were one-to-one and onto mathematical maps. We talked about two-dimensional rigid body rotations, two-dimensional rigid body translations. It is here that we had introduced homogeneous coordinates to express translation operations as matrix multiplication operations. We talked about reflection and deformation transformations like scaling and shear, and we generalized transformation matrices in both 2 dimensions and 3 dimensions. We subdivided a transformation matrix into 4 parts. The top left represented rotation, reflection, scaling and shear. The top right represented translation. The bottom left represented perspective transformation, and the bottom right, which is a unique single number, that represented global scaling, or it was also called the homogeneous coordinate scalar. Viewing. Why was viewing important? We wanted to comprehend or facilitate solid modeling. We also needed to communicate our designs with different people. Views were of 2 kinds, parallel and perspective. We talked about perspective viewing, orthographic projections, axonometric projections. Here we discussed 3 subparts: diametric projections, very popular isometric projections, and trimetric projections. We also talked about oblique projections, wherein we discussed cavalier and cabinet projections. Again, why would transformations and projections be important for us to study? One has to maneuver different primitives with respect to each other to perform set operations, for example, in constructive solid geometry, to build more complex solids. Many times one has to view a solid model from different angles, from different views, to doubly ensure that modeling is being accomplished as you desire. Transformations and projections, therefore, in my opinion, are essential and they should not be ignored. We now come to summarize the matter in the second column pertaining to curve models. We had spent quite a bit of time in this. We established that we needed a nice mathematical representation scheme, and we said it was the parametric representation scheme that was important for us. We studied differential geometry of curves, where we looked into Frenet-Sweat formulae. This was what we were going to be using later when considering continuity conditions at junction points. This is what the essence of curve model was that we studied. A curve was to be represented as a piecewise continuous composite curve. Each piece was a segment by itself. Each segment was a lower degree curve to lower the oscillations. And these 2 segments were juxtaposed at the junction points. And we needed the differential properties of these curves to address position, which is C0, slope, which is C1, curvature, which is C2, continuity conditions at these points. We looked at Ferguson or Hermite segments to start with. We looked at composite C1 Ferguson curves. This was an example. So composite C1 Ferguson curves exhibited local control properties. So if we moved one data point, only 2 segments associated with that data point changed in shape. And then we went on to study C2 or curvature continuous composite Ferguson curve. Here, this model did not exhibit local control properties. If I moved any design point, the shape of the entire curve changed. We were also, using this model, a little uncomfortable in specifying higher order inputs, for example, the slopes. We then decided, okay, we are going to be using only data points or design points or control points as input. That made things a lot easier from the user's perspective. With that in mind, we started studying Bezier segments. This was the algebraic form. The de Castelnau approach was the geometric form that we had studied. So we had a very interesting converging triangle type of technique to compute intermediate de Castelnau points. Here the idea was to combine different intermediate points via repeated linear interpolation. We studied wonderful properties of Bernstein polynomials that were partition of unity property and non-negativity property. Essentially, no matter what the value of the parameter u is, all Bernstein polynomials, they sum to 1, and all Bernstein polynomials are non-negative by themselves. It is the partition of unity property and the non-negativity property that made these Bernstein polynomials barycentric in nature. We had considered an example to see how barycentricity played a very vital role in designing Bezier curves. An important thing, any point on the Bezier curve is bound to lie within the convex hull defined by the corresponding design points, and this was the essence behind the Bezier curve models. We also studied subdivision, where given a Bezier segment, we could subdivide that in two different Bezier segments of the same degree without changing the shape of the segment by itself. The points in this slide which are shown highlighted, they corresponded to two different control polylines that defined two different Bezier segments. If you take a look at the inverted triangular scheme, the top edge comprises the points on the first Bezier segment, while the bottom edge comprises the points on the second subdivided Bezier segment in the subdivision approach. We studied degree elevation, wherein without changing the shape of the Bezier segment, we could keep on increasing the number of design points. We could keep on increasing, or we could keep on modifying our control polyline such that we got additional freedom in design. And then we took a look at composite Bezier curves. Here, for C0 continuity, the 2 points of two different control polylines should be the same. For C1 continuity, the common tangent should have the same direction, and for C2 continuity at the junction point, physically 5 points around the junction point and including the junction point, they should be lying on the same plane. They should be coplanar. Now, splines. Let me actually go back one slide and try to motivate as to why we had started studying splines. Let's take a look at one Bezier segment. If I move any data point, the shape of the entire Bezier segment would change. Not of the composite Bezier curve, but of the Bezier segment. We did not want this to happen. We wanted to give or impart local shape control properties to a curve model, and that's why we went on to studying splines. By definition, A spline is a curve which is Cn minus 2 continuous everywhere, where n is the order of the spline. So if you look at the bottom figure, we wanted to design bell-shaped basis functions, and we called each of them a B-spline basis function. It is the splines that we had actually spent quite a bit of time when covering this course material. We studied what polynomial splines were, and using polynomial splines, we attempted to design a very simple bell-shaped basis function. We were not very much satisfied, so we started exploring a little further. If you look at this figure here, we introduced 3 conditions on the left and 3 conditions on the right. What were those 3 conditions? The position, the slope, and the curvature at the 2 ends of a B-spline basis function. In this case, this is an order 4 or degree 3 B-spline basis function. All right. So the position, slope, and curvature were all 0 at the 2 ends. That made 3 times 2 equals 6 conditions. We needed one more condition to completely and uniquely determine a non-trivial or a non-zero B-spline basis function. The 7th condition was the standardization condition. That is, the area under the B-spline basis function was non-zero, and in fact it was equal to 1 over m, where m is the order of the B-spline basis function. So using the concepts of polynomial splines, we were in fact able to determine the mathematical form of this B-spline basis function. Each segment of this function was standing over each knot span, and at the junction points we had maintained C n minus 2 continuity conditions. So this was the generalized B-spline of order m. Throughout the time when we were discussing B-spline curves or segments or basis functions, I have been laying importance to the sketching of those corresponding curves. Let me summarize how I sketch a generalized B-spline curve of order m. I draw the vertical axis, I draw the horizontal axis, and I draw or sketch the B-spline basis function from right to left. I nomenclate my basis function as capital M sub small m comma I. I use 2 indices. The first index represents the order of the B-spline basis function, and the second index represents the last knot over which this basis function stands. So Ti on the right is the last knot, and Ti minus m on the left is your first knot. All the other intermediate knots will be Ti minus m plus 1, Ti minus m plus 2, Ti minus m plus 3, and so on up till Ti minus 1. If you get comfortable in sketching these B-spline basis functions, I assure you that you will not need to remember all the properties of the B-spline basis functions that we had discussed. These properties will be there in your hands. Anyhow, we figured that the polynomial way of computing B-spline basis functions was a little tedious. We wanted a little more formal way of computing B-spline basis functions. For that, we started off with the Newton's divided differences approach, and we considered the algebraic form, and we applied the Newton's divided difference approach to truncated power functions. Each truncated power function was a spline by itself. We had seen that. We established that a linear combination of these truncated power functions was in fact a spline, and we further established that the mth divided difference of the truncated function was in fact a B-spline basis function, and we had shown that in the corresponding lectures. We had a nice tabular form to construct B-spline basis functions. This was very similar to the de Casteljou's geometric approach when dealing with Bezier segments. To get the recursion relation for B-spline basis functions, we used the Leibniz result, and we had a nice looking recursion relation that related the order k B-spline basis function with two order k minus 1 B-spline basis functions, and then we had normalized our spline functions or spline basis functions. We looked at certain properties. The most important one were that all these B-spline basis functions, the normalized versions, they were non-negative, and not all, I emphasize again, not all but only a select few of these normalized B-spline basis functions, they summed to 1. And in fact, it was this property that imparted local shape control to B-spline curves. We had studied all that in detail. This is an important aspect of normalized B-spline basis functions. They impart strong convex hull property to the B-spline curve. We had taken an example. This was a control polyline, and this was our open B-spline curve. This was of degree 3 or order 4. So in a sense, you could have chosen 4 control points and considered a local convex hull defined by them. For example, for values of t in between 3 and 4, here values of 3 and 4 pertained to a particular knot span. For this example, this was the local convex hull. This was the second one. This was the third one. This was the fourth one, and so on and so forth. And this was the parent convex hull defined by all design points. Now, let me overlay all these convex hulls, and I would have you witness the contrast. So this is a very important point that I am trying to make. You look at all the convex hulls drawn previously, and then you look at the parent convex hull. What you would realize is there is a major area which is not common between the parent convex hull and the previous sets of convex hulls or the local convex hulls. Okay, where am I heading with this? All I'm trying to say is it's because of this strong convex hull property exhibited by B-spline curves that our B-spline curve very closely emulates the control polyline as opposed to a corresponding Bezier segment. Okay, so here's an example once again to show local shape control. This is our control polyline. This is our open B-spline curve, and if we move a point to a different location, only a part and not the entire B-spline curve changes in shape. So, we had also talked about multiple control points and multiple knots extensively in those lectures. And then we talked about a generic way of computing knot vectors. So, knot vectors were essentially based on parameters u, which were given by a plus b minus a summation, something in the numerator, something in the denominator. You would know how we had performed those computations. That is not of prime concern now, but what is of prime concern today is that we were able to come up with a scheme through which we could compute knot vectors in many different ways. For example, we used an exponent e, and for value of e equals 0, we came up with uniformly spaced knots. For exponent e equals 1, that was a quadrant parameterization, and for e equals half, it was the centripetal parameterization based on which we had computed knots again. So, this scheme essentially pertained or related to knot vector generation to compute again B-spline basis functions and therefore B-spline curves. Hows and whys of B-spline curves. Why should the B-spline curves be learnt in such detail? Now, this is an important question. It was more so a very important question for me when I, in fact, as a student and as a teacher, started learning B-spline basis functions and B-spline curves. I went through different books, and all they could help me with is through the recursion relation that is started with. I scratched my head quite a few times. I taught this course with that recursion relation, and I wondered how that recursion relation ever came into being. I started delving more, investigating more, and I looked at different cool methods behind that recursion relation, namely the use of Leibniz result, the use of truncated power functions, and the use of Newton's divided differences, how they play a very nice and a very vital role in framing up that very basic recursion relation that is used for the computation of B-spline basis functions. Now, that added a lot of insight as far as I was concerned. I personally felt it was a wonderful learning experience for me, and I wanted to share that with all of you. Again, being comfortable with sketching B-spline basis functions is what I have emphasized throughout, and I'll again lay importance to. But we have only learned just a little bit about those spline curves. How should I learn more? There are many more important things to learn about that we have not covered as a part of this course. For example, non-uniform rational B-splines or NURBS, knot insertion algorithms. Now, the knot insertion algorithm is something which is very similar to the subdivision algorithm that we had studied in case of Bezier segments. Blossoming technique. These methods were all ignored as a part of this course material. Interested users, students, and teachers are very much encouraged to study these aspects of B-spline curves on their own. For example, we can simply extend the rational Bezier curve model and apply that to define mathematically NURBS, or non-uniform rational B-splines. Now, if you try to relate those two expressions, the expressions are almost identical with a slight difference. There you are using Bernstein polynomials. Here you are using B-spline basis functions which are normalized of order p. That is the only difference. But there is a lot of physics and there are a lot of very interesting figures behind that simple relation. I would sincerely urge all of you to explore that aspect. There are many dedicated books, papers, and literature on NURBS itself. Okay, now to summarize surface patches, which is the last column in our layout. We started off with studying simple sheets, ordinary surfaces, singular points, regular surfaces, and we then diverted our attention on the differential geometry of surfaces. Here we encountered two fundamental matrices, matrix G, which was called as the first fundamental matrix, and matrix D, which was called the second fundamental matrix. It was the elements of the first fundamental matrix and the second fundamental matrix that were quite important for us in describing different surface features. For example, we could classify points on a surface as elliptic, parabolic, hyperbolic, or flat points, and we can also compute two different kinds of curvatures, the Gaussian curvature and the mean curvature. The mean curvature was the sum of two curvatures, and the Gaussian curvature was in fact the product of two curvatures. We then considered four different kinds of surface patches: tensor product surface patches, boundary interpolating surface patches, sweep surfaces, and quadric or analytic surface patches. Of these, we covered the first two categories in detail. In tensor product surfaces, we first covered Ferguson's bicubic patch, and then we did not like the use of the higher order, the tangent, twist vector kind of information, and then we switched on to bicubic Bezier surface patches, where we had only used design points, and then of course we extended that model to B-spline surface patches. In boundary interpolating patches, we studied quite a few models. The first one was a ruled patch that used only two curves as boundaries. The second one was a lofted patch that used two curves and information on cross boundary tangents at these two curves as input. And we had studied different kinds of Kunz patches, bilinear Kunz patch and bicubic Kunz patch. The mathematics, as you would have known, was quite involved. In both bilinear and bicubic Kunz patches, the basic idea was this: you frame two different surface patches, R1 as a function of two parameters u and v, and R2 as again a function of two parameters u and v, and subtract a surface patch R3 again as a function of u and v in order to meet the boundary conditions. We then looked into composite Ferguson surfaces using the F-mill method and composite Bezier surface patches. Again, what would be the kinds of questions that I would ask if I were you. Hows and whys. Let me admit that we had considered very simple surface models as a part of this course. Even then, the mathematics that we had looked into was quite tedious and intricate. It was quite involved, especially when we are considering composite surface patches. Many important models, for example, non-uniform rational B-spline surface patches, were ignored. Interested teachers and students are encouraged, and I would myself do that as well, to learn about NURBS surface patches on their own. Again, there is quite a bit of dedicated literature in this subject itself. If you think about it, all you would need to do is extend a Bezier surface patch into a B-spline surface patch or a NURBS surface patch only by replacing Bernstein polynomials with the corresponding B-spline basis functions, which are normalized and of order p. I wish it was that simple, but again, the features, the generality offered by this mathematical expression is huge. Just that little piece of mathematical expression does not do justice to the subject of non-uniform rational B-spline surface patches. As I said, there is dedicated literature available for self-exploration. You would note that neutral formats, which are used by many commercial softwares, for example, IGES, STEP, use NURBS patches to store, generalize, and transfer information between different existing commercial solid modelers. In a way, we are talking about unification here. I confess again that I did not tell you that I was going to be flashing about 100 slides. Let me repeat, 100 slides as a part of the summary for this course. This is one of the last slides that you would see. I have placed all the base material for this course in my home page. The URL is given by this: home.iitk.ac.in/tilde_Anupam. You click on courses and you click on the first course, and you will see that different PowerPoint slides are placed right there. I have also provided an extensive bibliography for this course for those who are interested in learning more, and I'll try to provide MATLAB codes for you to explore and have fun with. To conclude, finally, I hope you find this material useful. I would like to dedicate this video series on computer-aided engineering design to my parents, all my teachers, and to all of them out there who have made valuable contributions to make CAD much more understandable and amenable. Goodbye, good luck, and God bless. Thank you.